It's a real pleasure to be here. I haven't been here for quite a while, so great to see colleagues and to visit. And I have the opportunity to talk about volcanoes, so I'll try to entertain you with volcanoes in the next few 45 minutes or so. And we start here with a few of the pictures I've taken in the last 2 years. Actually, this volcano here was a picture from exactly, I think, the same day last year. I was with a group of students in the high Andes. We've been doing a cross-section from the Andes, from the basically the plutonic rocks that are to the south, all the way up to the high Andes and the volcanoes. This is actually the group. It's called Volcano Panorama Pass. And this is the place where we see the highest active volcanoes on Earth. This is Incahuasi, 6,600 meters, but behind here, peaking, unfortunately, we can't have a better view of it. This is Ojos del Salado, Nevada Ojos del Salado. This is the highest active volcano on Earth. And here is a picture for Olivier and Fidel. This is Sinabung for 2 years ago, without clouds, so a beautiful morning from the Sibaya caldera, just north of Lake Toba. And we have Sinabung smoking here. And this is another country and another climate. This is Iceland. This is Eyjafjallajökull 2 years ago, also usually in the clouds. But here we had a gorgeous morning. Here in red is Olivier Bernard and our Icelandic colleagues here as we are driving off the highlands. We're working on the volcano just a bit to the north at Törfajökull. So basically, I'll try to give you a tour on those volcanoes in the next few minutes. And of course, beyond their sheer beauties, volcanoes also have a lot of positive aspects. One of them, am I too far? No. One of them is, of course, that they provide us with a lot of critical resources. This is White Island in the Bay of Plenty in New Zealand. At the top of an arc volcano producing a lot of metals. People have suggested that in the last 10,000 years it's produced more than 1,000 tons of copper. And so this is an area where active ore deposits are formed. We've been also studying with my colleagues in the US and in Zurich, this incredible place in Nevada. This is the Yerington district. It's a porphyry copper deposit with the volcanic rocks on top and the plutons here all the way here. So it's a tilted section of a porphyry deposit that we can then study in 4D to look at the associated volcanics and plutonics. And we can date very precisely, so it's a very interesting aspect to see how magma chambers basically are degassing and producing ore deposits. But I also thought that we should mention that volcanic rocks are producing beautiful wine. I'm sure in France this is an important aspect to notice. This is actually Fidel, maybe you recognize this. I was a few weeks ago in Lanzarote. This is the Malvasia volcanica grapes that are growing in the highlands of Lanzarote in the eruption of 1730-36. Incredible. You see the not much humidity and a lot of wind, so they shelter those vineyards behind those walls, but it makes an incredible wine. They also produce a lot of energy. This is the colors here are not giving you the right color, but this is the Blue Lagoon in Iceland. This is the #1 touristic spot on the Reykjanes Peninsula, but it's basically the dump waters of the power plant behind. And so the silica is crystallizing on the black basalt now, but all the water that you see here is basically coming out of the geothermal power plant that's super active behind, producing a lot of the energy for Reykjavik. And this is one of the beautiful hot rivers in Iceland coming out of the highlands from Torfajökull. And this river here is wild. There's almost nobody here, but it's 40 degrees C, and so you can have a bath in the hot river. I prefer this hot spring than this one, but most people are actually going to this place. And of course, this geothermal energy is a wonderful opportunity for us in the 21st century to get cleaner energy. This is an incredible source of energy. It's active 24/7. It's there in different sources and ways, and so a lot of governments now hopefully will be pushing this. New Zealand has been very active in developing this, and we've had a PhD thesis in the last years with our colleagues in New Zealand to try and understand the interface between magma chambers and the hydrothermal fields on top of this. And so that's been a very interesting journey that I have done also in the last few years. But the problem, of course, is that volcanoes can produce too much energy sometimes. As we all know, this is the energy produced by different natural phenomena and not so natural phenomena like the atomic bomb, but you see that Mount St. Helens 1980 and supervolcanoes are the most energetic natural phenomena that our planet can produce, only matched here by large meteorite impact, but of course the meteorite impacts are much less frequent than those supervolcanoes. And so just as earthquakes, volcanoes can be classified as magnitude, or what we use as volcanologists is this volcanic explosivity index. You've probably heard of it. This is basically a volume scale with the VI0, which are very small volumes, to the VI8, which are volumes over 1,000 cubic kilometers of erupted material. And so here we have examples here. Mount St. Helens is a typical VI5, and supervolcanoes are classified usually around VI8. This is their definition. So this scale of ranking volcanic eruptions is basically a volume scale, but there's also an aspect that comes is that generally we have more gentle eruptions in the small VIs, which are more typically effusive, and then towards the higher VI we have more explosive systems. But this is not always true, as we'll see in a few minutes, but generally this is the case. Up, there we go. And so, of course, this energy can lead to deadly situations, and we all know this is the deadliest eruptions in history, including the Montagne Pelée here, 30,000 people killed in a few minutes in 1902. So, of course, what do we do to mitigate those effects and avoid such tragedies in the future? Of course, this will happen, and we have to do something, of course, to try and understand our volcanoes better. So, obviously, understanding volcanic system and reading the signal of reawakening volcanoes is what we try to do, but how do we do this exactly? And here I've been asked also to show maybe a little bit of what happens over this last decade. So I wanted to show that we've made amazing progress, and I'm sure most of you working on observatories know that indeed over the last century we've made amazing progress at monitoring volcanoes. There's many examples here. I chose, for example, the 2021 La Palma, where the outbreak of the eruptions was predicted wonderfully by many aspects of the volcano monitoring, but certainly the seismic sequence here that the eruptions happened on the 19th of September here, but starting on the 12th of September we have this cluster of deep earthquakes that then migrated to 10 kilometers where the shallow magma chamber was, then it stayed for a while and then migrated up and erupted on the 19th of September. And here we see I have little videos. I don't know if some of you saw these videos, but it shows beautifully this. Come on. Yeah, this sequence of earthquakes migrating up towards the red point and the eruption site, which is this. Sorry, a bit difficult here. Oh, the eruption site is here, but. Voila, it goes up, and you can see migration of earthquakes going up. So now with this monitoring, we can, of course, see these outbreaks quite well. Another experiment that we're having is now the Reykjavik Peninsula. I'm sure most of you have followed the the activity on the Reykjanes Peninsula in Iceland. Here's the map, we don't see it, but this is the area. The airport of Keflavik is right on this peninsula and not very far away. We have this extreme activity in the last 5 years or so. Beautiful time series of earthquakes, great vertical displacements, amazing pictures with drones. Very interestingly, this summer I was doing field work there, and we were eating next to the Blue Lagoon, which is right here, and there's a big restaurant, a hotel, and all the volcanologists were saying, okay, eruption imminent, but everyone else was working as normal. The tourists were coming, the Blue Lagoon was open, and the eruptions occurred a few days later, but clearly our colleagues in Iceland must be confident that they know where it's going to happen to allow those big tourist infrastructures to be active when the eruptions is coming. So quite impressive how we can do this, but of course this is not always that easy. There are volcanoes that are not behaving as well, and here you'll allow me to use this very oversimplified characterization of volcanoes to discuss these aspects, but we have those so-called red volcanoes that produce basaltic magmas where gas can escape easily. We have low primitive magmas, basaltic, with low temperatures, low gas content, low viscosity, and for those determining the outbreak of an eruption is fairly easy. However, we have, of course, other volcanoes, the gray volcanoes, with more differentiated magmas, andesites, up to rhyolites, high gas content, much higher viscosities, and of course those ones are very difficult to predict. So I'm just showing here two volcanoes, some of the great volcanoes. Mount St. Helens 1980, that had a complex sequence with beginning of the outbreak of the eruption in early March, and then the eruptions, the Plinian eruption that happened in May. So the sequence was not very well understood, and of course that led to casualties. A lot of people died during these eruptions, and it was not predicted well at all. Then a case probably that some of you know, is the Soufrière de la Guadeloupe. We were up there with the family a few years ago. It's all quiet now, but in the 70s, that wasn't the case. I was very active, and probably all of you remember that there was some quite tension and controversies around these eruptions. Will it erupt? Will it not? And of course, the IPGP was strongly involved, and I'm quoting here one of the big protagonists of that discussion, Arun Taziev here, that said a lot of things, some good, some less good maybe, but very interesting anyways. I'm quoting here at least some interesting aspects of what he says, is that for those gray volcanoes, forecasting the outbreak of an eruptions may not be the most useful thing to do, because obviously the paroxysm occur not at the start but during the development of eruptions. And what might be more important is to try and predict whether an eruption will culminate into a climax, so making a very large eruption, and if so, of what type of eruption we might have. Should it be explosive or effusive? And something that he also pushed was to say that, okay, one of the main driver of volcanic eruption is the gas phase, and of course it's highly compressible and highly energetic, and there should be effort to try and understand that, even though it's very complicated. In looking at this and thinking about the future, is there any hope that we can ever predict the style of a gray eruptions and try, if you remember, trying to forecast basically the VI, the volcanic explosivity index of a future eruptions, and for us, how to look for potential future Tambora or Toba. So clearly, one thing that seems to be quite important to me is to look at what happens underneath those volcanoes. As those volcanoes are the tip of not an iceberg, but a heatberg here with a big plumbing system underneath them. They have very complex plumbing system with complex multi-phase mixtures of melt, crystals, and gases at different levels, magma chambers throughout the crust or a certain level inside the crust, but clearly we don't understand this very well. And for us, very important is to try and to determine the shape, size, and states of those reservoirs that control a lot of things, from the geothermal energy that can be released to, of course, the type of eruptions that we can have. And of course, also, it allows us to understand how crust differentiates, how we produce all sorts of magmas from the basalts to the rhyolites. And here also with this, to think about what we can learn from plutonic rocks as well as volcanic rocks. They're both magmatic, they're all igneous, and both should tell us a lot about how our igneous process work inside our planet and other planets. So looking at these interactions between volcanic and plutonic, this volcanic and plutonic connection is also for me been quite interesting in the last few years. So those early drawings of plumbing systems have been interesting for quite a while. People have been trying to draw those try to image those crustal sections for quite a while. This is two examples from the 1980s, early 1981, just after the eruption of the Mont St. Helens, from Jim Gill and Wells Hildreth. You see very different styles. Since then, we've done a lot new ones here, potpourri of some of those. There's also we've all tried to do something. You can see some similarities, some dissimilarities. There's even the one from Fidel and Olivier here from Rabaul. Obviously, we don't really know. And we're trying to get this a bit more precise. But clearly those plumbing systems are a great interest, but we need to get a better focus on how it actually is underneath those volcanoes. And so what I'll try to do now is to focus down on two questions for the next 20 minutes, and two fundamental and related questions that are also linked to this VI scale, and try to understand what happens in those reservoirs. The first question that I will try to ask, or actually the second here, will be thinking about eruptive style. How can we understand or predict future eruptive styles by looking at those plumbing systems? And I call this question flow or blow, meaning that we will have an effusive eruptions, which is usually less impactful for the society, or we will have an explosive eruption that, on the contrast, can have a lot of impact on people living around. And the second question I wanted to briefly touch upon is to have this VI scale, starting from small eruptions to very large eruptions. We need to find a way to make those magma chambers grow. What makes those magma chambers grow to supersize, and how can we understand physically whether the system will grow a magma chamber or will blow, and meaning erupt, and that feeds into this volcanic plutonic question. Okay. So briefly also, volcanology, as many of our earth science perspectives, are sort of coupling two complementary research philosophies. Of course, I'm coming from the side of looking at rocks and doing petrology and going into the plutonic record or the volcanic record to try and learn about past eruptions. Recently, I've also worked a lot with geophysicists to try and image volcanic plumbing systems with seismic tomography, with MT imaging, looking at boreholes also. It brings us, of course, a lot of information. But to be more predictive and more physics-oriented, I think now we're getting also to the point that we have a modelistic view that develops, and also now a database view. So a lot of observations mixed with models to try and help us understand the evolution of this complex natural phenomena that volcanoes are. And I will try to mix both today, and been trying to do this over the last few years. So let's start with the first questions, the grow or blow. How do we grow magma reservoirs in the crust? As I think now the community largely agrees that This is a process that occurs slowly over time, incrementally, one pulse at a time, over decades, centuries to millennia for the largest. And to represent this, I'm using here a small computer simulations from one of my former students, Sarah Gelman here, who just shows a conduction model here of the growth of a magma reservoir by formations of sills in the upper crust. So what you see here in color is a block of crust, 20 kilometers deep, over 5 kilometers wide. And you see it's cold here in the upper parts in blue. The colors, of course, the colors cold here, warmer and at depth here with the geothermal gradient. And we inject here magmas that are 1,000 degrees at 5 kilometers depth. Okay, and so we can see that as we inject this, we'll have a competition between cooling and recharge. And at a given amount of recharge, we will be able to keep the magma reservoir alive. So, but what we see at the beginning, here is that here is you see the sills are coming in, and of course they cool in the cold upper crust. But as they get more, as you stack those sills, they start making a red balls or warmer reservoirs. They're still cooling mostly and getting under the solidus, so they crystallize to plutons. And you see when it starts going down, it means that basically what we're doing here, we're underplating the sills. And so when they're going down, it means that there's a part of the reservoirs that stays molten. And basically that means that in between injections, we have reservoirs that is kept alive. And so basically we do have a long-lived reservoir in this situation, okay? So I think this is a way to image an analogy of, or maybe the mechanism how those magma reservoirs grow. Here you see that basically the crust here, and then now the simulation is finished and it's cooling as the system is over. But you see that there's this competition between cooling and recharge. To keep the reservoir alive. The reservoir will be mostly kept as high crystallinity, as a mush. But what we don't see here with this model, of course, is when does it erupt. This is a simple conduction, thermal conduction model, and it doesn't tell you when the system erupts. To see it erupting, you need to have another aspect, which is how does it pressurize inside those reservoirs. And for this, we need a bit more complicated model, and this is, for example, one of those models, or I guess the only model out there now that actually tracks the pressure inside those reservoirs. This is from De Gruyter and Huber 10 years ago, thermomechanical model that can track the pressure, temperature, water content, volume, mass injection rate of magmas in this simulated reservoir that is open to recharge and allows eruption. So the magma reservoir is coupled to thermodynamic models that allow to have crystallization and volatile exsolution, so we can have the three-phase inside. It is linked, coupled to a viscoelastic crust that is temperature dependent, and then we can control the recharge inside the magma reservoir, and then we have eruption when the pressure inside the reservoir reaches a certain threshold. Okay, so we can choose that threshold and say, let's say at 10 megapascal or 40 megapascal, pressure is too high, the crust around will crack, and we have the beginning of a dike and an eruption. Okay, and then we have outputs that we can have time series of the evolution of pressure, of temperature, of the volume of the magma chamber, phase fractions, etc. So this gives us an interpretive tool on how volcanoes may behave if we know certain of those parameters. The type of recharge we can use also are complicated. We can use different recharge rates, recharge periods, and that allows us to change those parameters to see how the magma chamber reacts to this recharge. Okay, and just an example here for to show you when we change the recharge, what it gives in terms of pressurization. So here we have 3 simulations. We start with the same parameters, input parameters. The magma chambers are all the same, 50 cubic kilometer. and it has those bubbles here indicate that it's gas saturated, so it has a few percent bubbles. Then we have the red and the blue simulation here that have recharge rates of 0.05 cubic kilometers per year and recharge durations that are slightly different. The red one is longer than the blue one. And then we have the pink one in the middle here, which has half the recharge rate, so slower recharge, but the recharge duration is longer. Okay, and what does it do in terms of pressure? So this is the graph that shows time since the beginning of recharge, which is here at 0, and the overpressurization inside the magma reservoir. And you can see that here in this case, only the red one reaches this 40 megapascal threshold that we have. The only one that erupts here is the red. The two others are basically producing a growth, net growth of the magma chamber because they pressurize it, but they don't reach the eruption, and hence they added material in the reservoir, okay? So here we can see how recharge, the type of recharge we have, can lead to an eruption or to a growth of the magma reservoir. And when we have eruption, volcanoes that are restless, that are shaking but not erupting, most of us think that we have this case, and the magma is replenished by some recharge, but doesn't reach the eruption threshold. The other thing that we found that was super interesting and very impressive is the effect of a gas phase, so an exhaled gas phase in the magma reservoir. That has a huge influence on the pressurization. Here again, two similar simulations starting with the same volume. But one has no exhaled volatiles before, and the other one has 2 or 3% of exhaled volatiles. So very little, but it has a few of the bubbles. Here we use the same recharge rate and duration, and here you see the same plot, time since recharge and the overpressurization. And here you can see that the orange one, the one without exhaled volatile, pressurizes very quickly and reaches the eruption threshold, whereas the green one here has the buffering capacity of those volatiles. This volatile phase is very compressible, and when you recharge it, you add mass, the pressure can be buffered by the presence of this compressible phase. It redissolves and allows the pressurization inside the magma chamber to become less important. So it doesn't reach an eruption threshold and allows the magma chamber basically to swallow that injection and grow. Okay, so we can do those simulations run very, very rapidly. We can do several a day. And here are some regime diagrams to try to understand this question of grow or blow. Will a system erupt or not? We can use thousands of simulations and come up with those regime diagrams here, trying to play with the main parameters that we have for this question of growing magma chambers, which is the timescales of cooling, injection, and then the crustal relaxation. So how accommodating is the crust around to make room with this new magma coming in. So here is the x-axis is the competition between the cooling and the injection timescale, and the y-axis here is the relaxation time of the crust over the injection timescale. So just to help you a little bit understand this is quite complex and rich here, but basically on the right side of the diagram, we have rapid injection, so systems that are injected very often, whereas on the left side here, we have system that is slow injection rate, and so cooling wins, and we have rapid crystallization. And then the upper part of the diagram is where the crust is more elastic, so it responds brittly by cracking, and so eruptions are so basically it's much more difficult to make room, whereas here the crust is more viscous, ductile, and allows to swallow those magmas. So if we start with the R1, here is the first region where we have eruptions basically mostly in the part of the rapid crystallization. Also the colors here are the number of eruptions that are computed by the simulation. So in red here we have lots of eruptions, in blue less, and black no eruption. Okay, so the part where cooling dominates here, we have a few eruptions that are mostly dominated by second boiling, which means that the system is crystallizing, it's exsolving volatiles, and of course that increases a bit the pressure, and sometimes the eruptions happens. Okay, but they're fairly rare. However, if we have a system that's dominated by injection here, then the system is pressurized very, very often, especially if the crust is ductile, and that leads to a lot of eruptions and low growth. Okay, and then if we look at this bottom part of the diagram where the crust is viscous and very accommodating, here for a wide range of injection timescales, we can see that we have a region with no eruption at all, and this is where we have this intrusive phase where the magma chambers can grow. Okay, so now for our magma chambers, how do we reach supersize? How do we understand to make a Toba or Tombora or Bishop Tuff or whatever, a supervolcano with your favorite supervolcanoes? You imagine that you need fairly high injection rates, so high fluxes, but you also need those magmas to stay in the crust. So the real key aspect here is right here, where we have high enough injection rate, but not too high for the system to erupt. And so this is the area where the crust, the magma chambers are growing the most. And here is a zoom on this area where we computed magma chamber growth rate by mass on this regime diagram. And you can see that it's falling here, right in this corner between the plutonic area and the injection area here, so R2 and R3. And we've plotted here also caldera systems on this regime diagrams, and you can see that they fit right around this area as we would expect. So here to summarize here, to reach very large magma chambers, important is to have a crust that is as accommodating as possible, and so we need a warm crust where the viscosity is less and the magmas can be swallowed inside magma chambers. We need high injection rate because otherwise the system dies and cools, but not too high, otherwise the system erupts. And as we've said, is the presence of an exhaust gas phase is massively important. And so the systems that are gas saturated are probably the ones that are going to make the largest magma chambers. And so for us, as petrologists and volcanologists, maybe this is one thing that we should look into is where are the magma chambers that are gas saturated and what does it mean? Where do we need to see overall in the whole magma chambers or in some parts of it or something I still don't know. So anyways, the summary here, ingredient to build supervolcanic magma reservoirs, incremental growth, of course, with high flux, but not too high. And how to make the room for the reservoir to grow. We need this thermally mature, warm crust to allow more ductile behavior, and then, when possible, having this compressible gas phase in the reservoir. And that might help us already understand the behaviors of volcanoes. Two of my favorite Cascade volcano. This is from Mont Rainier, from my house in Seattle. When we were living there, we could see Mont Rainier every day when the weather was like this. Of course, it's not always like this, but Mont Rainier has produced a lot of frequent eruptions and built huge mountains, but never erupted a supervolcano. It's just making small eruptions over and over and over again, making a huge mountains, whereas Crater Lake, just a few 100 kilometers to the south, has produced this massive caldera. And so clearly this one has been able to build a large reservoir, whereas this one not. Okay, now we change for the last 10 minutes here on the second question, which is close to my heart, also something that I've been working since the beginning of my thesis that's very interesting, I think, is why do volcanoes switch eruptive styles sometimes, clearly, without telling us, and we would like to know. And one of the best examples of that is in the southern Andes. It's this volcan Quizapu here with a picture of the two brothers. Actually, this is Descabrizado Grande and Cerro Azul, and Volcan Quizapu is located here. There's a huge basin here that is filled by two big eruptions that are one explosive and one effusive. And I'll show you, this is my former PhD student who worked there, Philipp Ruprecht, carrying one of the pumices from the 1932 eruption. I think, here is the southern Andean volcanic chain with all the volcanoes that we have as the Nazca plate is subducting. Quizapu is here. I needed to put another volcano here, Tatara San Pedro, just for Fidel. Fidel did his thesis in Tatara San Pedro. Quizapu is just north of it. here, and a wonderful place, and very interesting for these questions because it produced two eruptions in historical time. One in 1846-47, and it produced this massive lava flow, 5 cubic kilometer, completely effusive, no associated explosion, so a very thick lava flow. And then the volcano paused for 86 years. And then in 1932, without much warning, as far as we can tell, it produced a Plinian eruption of the same size, of the same magma. Everything is the same mineralogy, same crystal content, same composition. But it switched in 86 years, the same volume here, completely different eruptive style. And of course, the second one here, the eruption reached Buenos Aires and covered most of South America here with ash, whereas the first one was barely noticed by the locals because it just filled the area. Here is the location here. You can see the lava flow here, 400 meters thick in some places with those big spines, and then it's covered with the ash and the pumice from the 1932 eruption. So most of us learn volcanology by saying, okay, well, basalts, low viscosity are effusive. Here's Kilauea or Reunion Island. They're producing those beautiful streams of lava flows. Whereas the gray volcanoes, viscous, gas-rich, arc volcanoes erupt, Soufrière Hills or Soufrière or Montagne Pelée, etc. However, as we were discussing this morning, and as probably most of you know, this is not always the case. There are many high silica, rhyolite, viscous, water-rich magmas that erupt effusively. And here are a few examples, including the spine here of the Montagne Pelée, but the famous obsidian flow in the US. This is the largest quaternary lava flow in Chile, Chaude site. The beautiful Yali Island here in the caldera from the Cos Neceros. So many of those effusive eruptions of viscous, water-rich magmas. And how is that possible? Obviously, if we let it go and we keep everything together, we should have an explosive eruption. In a closed system, the magma comes up, degasses, bubbles up, foams up, and it will will accelerate and reach fragmentation at some point. However, in those effusive eruptions, we need to have this gas coming out. And for this, we need somehow to build up permeability in the magma. So the magma has to let the gas go and basically manage to open a permeability system, so increase the permeability inside the conduits. However, those conduit processes are, as most of you know, and you know, most of the community has been trying to think about this, is very complicated, super difficult to model, it goes super fast. And so even if we could predict what happens, we have very little time to act and mitigate. So one of the questions we were asking is whether magma chamber conditions help us understanding what will erupt later, and whether we can, by looking at magma chambers where we have more time to monitor and look at things, whether this also contribute to determining whether a volcano will erupt explosively or effusively. And so this is actually a COVID project. Well, we couldn't go anywhere. We were stuck on our computers. We had at least internet. So a postdoc and I started to compile a lot of information about published silicic volcanoes all around the world. Here we compiled more than 250 units by looking at their compositions, their water content, their crystallinity, and we're trying to make that simple plot. I mean, basically dissolve water content in the magma and crystallinity as a function of composition. And what came out is this very striking graph, is that we have this blue here, which is the explosive units that are in the middle here, making a little window, and then all around them are the effusive units. So we're trying to figure out what happens if this is true, and how could we, if yes, can we explain it? So this graph is now very busy because of all the different units here, but it's capped here by the rheological eruption limit. So at more than 50% crystals, usually magma don't erupt, they're too viscous, and so we have nothing above 50%. And here is, we don't go much higher than 6 to 8% because this is clearly the solubility limit of water in the upper crust. So there's a lot of, and we have a full paper on this, but I give you the primer and happy to discuss this more later, but here are our hypotheses as to why that is the case. So to explain the effusive units, of course, if we go to low water content and low crystallinity, we have the classical explanation. This is low water content magmas, they're less explosive, and that's what we expect. This is the first, the volcanology 101 idea where things are a little less fast, buoyancy is lower, and the system is more effusive towards low water content. At high crystallinity, we think it's also fairly well explained. What happens there is that you have a lot of crystals, maybe up to 40 to 50%, and the gases that are inside, when they go up, first of all, the ascent rate is low because the viscosity is quite high because of all those crystals, but also the gases don't like to touch the crystals. And so there's this non-wetting gas phase that will be then squeezed in between the crystals, and it will make those channels. This is quite well predicted by fluid dynamics simulations. There's this effect of crystal confinement that led to very efficient permeability development. And so when we have a magma that's very crystal rich and goes up the conduit, it tends to develop permeability very quickly and can degas. And that's why we have a lot of crystal rich andesites and dacites that are lava flows. The more difficult part is, why do the most water-rich magmas and crystal poor also erupt effusively? Think about all those obsidian flows that we see in Iceland or in arcs in Oregon. And what we think here is back to this compressibility issue. What happens is that when we have a system like this, maybe I'll go to, this is where Kizapu is, and so I'll give you a quick rundown of the model, what we have for Kizapu, and for those crystal poor, very water-rich, high silica rhyolite magmas, or high silica dacite in this case. But what happens is that for the effusive eruptions, and notice also that it started with this lava flow, and not the contrary. It started with the lava flow and finished with the explosive. Again, counterintuitive. Most people would have put the explosive first and the lava flow after, saying, okay, well, the magma degassed and it became effusive. But not at all. It's the opposite. And here, what we had is, so we had a system that was quite compressible. It was open to recharge. The lava flow is full of beautiful mafic enclave of andesite at 1100 degrees. So clearly there was a lot of magma that came in, but it was compressible, so it allowed more recharge to come in. This led to an important reheating that we can measure petrologically. The oxides are very hot, so we can see that the magma got heated up very much by about 100 degrees before eruptions. This led to lower viscosity melt, and also we had bubble present at the base of the conduit, which led to more efficient eruptive degassing due to those situation of lower viscosity and the presence of a bubble. But this eruption, of course, degassed the whole system, and then we reached the situations where we got back into this eruptive window between 4 and 5 weight% gas. Here the magma was not compressible, didn't get reheated so much. There was no nuclei of bubble, and the system ramped up to a very explosive eruptions. So this is our conceptual model for now, something that we would like to test in the future, but a very interesting aspect for the future and hoping to predict those eruptions is whether, if this is true, that this is controlled partly by conditions in the magma reservoir, is there hope for us to in the future trying to predict whether a system is gas saturated or not, and help us better predict the style of volcanic eruptions in the future. So if we go back now to the first questions, how do we tie certain aspects of what we learned about this plumbing system to VI, so the size and the style of eruptions? So the size, we think that we can reach supersize in areas where we have long-lived magmatism that warms up the crust. It has to stay in the same place with a high flux, but not too high, and the presence of a gas phase in the reservoir. And In those areas, we also, for the eruptive star here, the diffusive behavior is seem to be enhanced by high crystal content and on the presence of an exalt gas phase in the magma reservoir. So one fundamental parameter that I don't know if we've thought about this enough, but it seems very important, and we need to better understand this, is reservoir compressibility. So with geophysicists and deformation studies, MT, magnetotelluric, or seismic studies, is there ways to better understand the compressibility of those plumbing systems and to give us better images of the size, states, and depth of those reservoirs and try to connect to the roots of those volcanoes to better understand them. So now the last 3 slides to give a bit of my feeling as to where things can go. So of course imaging those plumbing systems seems to be very important, and we've tried to do this now with a big group in the USA in the last few years, a project that was called IMUSH, for imaging magma under St. Helens. And so we went to Mount St. Helens and did a lot of different techniques. We had an active source tomography with dynamite shots to try and see the upper and lower crust, and we see that we can get very good images of a lower crustal reservoir and an upper crustal reservoir. We did a very large 3D MT experiments and a lot of petrology and geochemistry and dating, also to really look at the evolution of Mount St. Helens in the last 10,000 years. And since it was a very large project with dynamites, people were interested as to why we would bomb Mount St. Helens. And so we tried to do a lot of outreach and draw such simplified diagrams to teach to the press, and had quite a bit of media attention. And this is where things went wrong. When you ask a scientist to talk to the press, we oftentimes don't do the right way. And this image, for example, came out in a newspaper in Seattle, and then the next day the British tabloid got that one here as a Mount St. Helens will super erupt very, very soon. So we had to do a lot of damage control after that to say, no, that's not what we meant. Those big red blobs here are not super large reservoirs. They're mush and they won't erupt, don't worry. And so it was a rich learning experience for us as scientists, and something that I learned a lot on how to try and communicate information to the public. I'm sure that you all working in observatories know much better than I do, but this was my first. And so this is then we had to do a revised version of the also published in Scientific American a few years later, to try to explain much more in detail. So we had to put crystals in there and small reservoirs, and anyways, very interesting. Those reservoirs also are key to all sorts of volcano monitoring and volcano predictions. And what I think is very important, and many of you also work, is to try to understand where are the eruptible domains in those complex plumbing system, what are the mechanisms and the rates of generating eruptible pockets. Fidel has been working and all his group for many years on this, using different techniques of geochronology, of geospeedometry, trying to see how quickly those systems react to recharge or changing conditions. Those systems are, as we said, mostly crystal rich, and so the dynamic, the physical behavior of those magma reservoirs is of course extremely complex, and we need to understand this rheology of mush better. And I think that also I find particularly interesting in the last few years. Also, I've been working in Argentina, where we have sections now in the Earth's crust where we can see those crustal columns tilted on their sides, and we can walk from practically the mantle all the way to the volcanoes. So we can see the lower crust, we can see the mid crust, we can see the upper crust. All the plutons are there. We can analyze them. It's extremely complex, but those exhumed crustal sections can probably teach us a lot if we can mix this with the models and the monitoring that we do. So those give us, volcanic plutonic ratios over time, mechanisms for differentiation, And then we can calculate rates. And then also for volatile cyclones, and if we couple back to the ore process and how do copper and sulfur and gold are being circulated into those igneous distillation column, it's quite a place to do this. And finally, also, maybe some of you have heard of this, and planetary sciences are taken on as never. A lot of people working on volcanology and igneous processes on other planets. Recently, I've seen that also some of you are interested in the InSight missions on Mars. We've had a PhD student working on trying to understand the stability of magma chambers in the Martian crust. Underneath the large volcanoes, but also in the two different hemispheres. So also I think a very interesting future directions to understand planetary volcanism. And I think, last thing is that some of my groups are over the years who've contributed a lot to what I've said today. Of course, have to thank them all for all the efforts and the great discussions. I think that's it. And so if you're not frozen, thank you very much. And you can move a bit now.